Okay, so we see that once you've got the surface parameterized, it's fairly straightforward to just calculate your TU and TV vectors, take their cross product, and integrate the magnitude of that cross product. Okay, big question then is how to parameterize various surfaces. So let's just do a couple more examples. If you have a cylinder of radius A and height h, how can we parameterize that? Okay, now we're not talking about the interior, we're talking about the surface of the cylinder, and specifically right now, let's say the curved surface of the cylinder. Well, that's pretty easy to parameterize actually, because every point on the cylinder lies vertically above a circle in the XY plane. And I'll comment, it doesn't have to be the XY plane. I never said where to put this cylinder. You could rotate the thing so it's not, its base is not, its axis is not parallel to any plane, any of the coordinate planes. Or you could rotate it, like lay it on its side so the XZ plane is perpendicular to the axis, so that the y-axis would be the axis of symmetry. Or you could orient it so the x-axis is the axis of symmetry. Since we generally think of functions that we graph in terms of a base on the xy plane and then the height of the function being above the xy plane, we're going to go ahead and do it this way, but there's no reason not to do it in one of the other ways, and you'll encounter that in your homework. Okay, so cylinder of radius A and height h, you're going to say, okay, well, let's parameterize the circle of radius A, and that's very straightforward. X equals A cosine u, y equals A sine u, u from 0 to 2 pi. Other parameterizations are possible. Like, as you've seen, we could have used u squared and a limit of square root of 2 pi if we wanted to. We're going to let then the cylinder go from the x-axis up to height h by letting z equal v and v going from 0 to h, so that you get any point on the circle with this parameterization, and then you go to any height between 0 and h with z equal to v. Then your r vector is a cosine u I plus a sine u. I don't have to read it. There it is. This times I, this times j, this times k. Your parameter space is, got hung up on that 9 there, didn't I? Parameter space goes from 0 to 2 pi along u, from 0 to h along v, and the area multiplier is the magnitude of Tu cross Tv, and Tu is just, take the derivative with respect to u, you're going to get negative a sine u times I plus a cosine u times j. There'll be no k component. Put that into your determinant. And then you take the v derivative, which is just going to give you 1. Then your Tu, oh, well, 1k, it's just going to give you k. Your Tu cross Tv is then going to be very straightforward, very easy to calculate. Don't really even need the determinant. You can use the distributive law. You're going to get what? You're going to get negative Tu cross Tv, so it'll be I cross k, which would be negative j. So you're going to get sine u j plus cosine u, say k cross j, negative I, minus cosine u j. Magnitude is going to be 1. And you, is that right? Yeah, calculate it. Anyhow, you're going to get this. Magnitude is going to be 1, and sorry, magnitude's going to be A, and when you integrate then, you're just going to integrate A with respect to V and U, V going from 0 to H, U going from 0 to K, which is going to give you 2 pi A times H, which is exactly what you should get, okay, because the radius of the base is A, its circumference is 2 pi A, its altitude is H. If you cut this thing and flatten it out, you get a rectangle of dimension 2 pi by H. So that one's particularly simple. You want to do the upper hemisphere of radius A centered at the origin, and go ahead and do it above the XY plane. You could do it to the right of the XZ plane or in front of the YZ plane if you wanted to. Just change the parameterization a little bit. You can parameterize the hemisphere again by x equals v cosine u, y equals v sine u, which gives you any circle in the plane. We let u go from 0 to 2 pi. We're going to let v go from 0 to a because we want these circles to go out to the radius of the hemisphere. So that gives us the circle of radius a in the plane. And now your z has to go from this to this. Because, why? Because if, okay, down here, this is some section of the xy plane here. Here's your value of v. Okay, this is how far you are from the origin due to this part of your parameterization. Now you've got to get to the sphere, which is up here. Distance from the origin to the sphere is a, the radius of the sphere. The distance in the xy plane is v, so that distance you've got to go up here by the Pythagorean theorem is the square root of a squared minus v squared. It's a really bad square there. Let's see if I can make it worse. Yeah, I did. Okay, chalk just doesn't want to cooperate. Let's see if I can make that. At least that's better. Okay, and then down here, you, of course, if you wanted to go to the whole sphere, you would go down to here. Okay, now we're only doing the upper hemisphere, as we can see by, well, so we're doing the upper hemisphere, but now I've let z go from here to here, which takes us through the whole sphere. So, let me change what I said here. I'm going to wipe out hema, and it's the sphere of radius a. We can do that. Have the parameterization. Here's our parameter space. Here's our R vector. Do our 2u cross 2v, and integrate accordingly. Okay, that's going to work.